So I say it's 3:30, so we can start now with this session, which is about innovative business models for European PV solutions. Welcome to everyone. This is Monica Lehmann from the Becquerel Institute. I'll be doing the moderation for the session today, where we will have 3 Horizon 2020 projects, which will be sharing part of their learnings. First one is BIPV Boost, where the target is about bringing down costs of building integrated photovoltaic solutions and processes along the value chain, aiming to enable a widespread zero energy building implementation. This project will be presented by Elena Bosch. Elena has a master's degree in energy engineering from the French engineering schools, Mines de Douai. She's also working at the Becquerel Institute since 2 years, where she's a business analyst. She's working with consultants in missions and research projects at the Becquerel, especially on topics linked to building integrated photovoltaics, battery energy, stationary storage, nearly zero energy buildings. She's mainly working on techno-economic aspects in these projects, including competitive analysis, market potential estimations, cost evolutions modelings, on short to long-term or business model assessment. Then we will have the project EnergyMatching, which will be presented by Fabricio. Fabricio has a broad experience in project management, dissemination, and exploitation for the EU programs, both for local development and research innovation. And he's also working on proposal preparation and research activities in public policy, media, and corporate governance for public institutions and multinational companies. He graduated from Economic Geography and Territorial Processing at Bologna University. And after that, he did a master's in EU projects at the Salento University. Fabricio is mostly interested in economic, social, environmental, and technological aspects of sustainable development, as well as digital and social innovation. Finally, we will have the project Super PV, which will be presented by Dr. Thorstein Harberg. He's the founder and managing director of BIPV Energy. It's an SME which has been established in 2014 in Norway, which is assisting customers in techno-economic and environmental variability of new opportunities in the circular economy and the fast-changing energy markets. Mr. Harberg received a PhD in organic chemistry at NTNU Trondheim in 1989, before working for Norsk Hydro until 1997. Then he worked at Hod Herald Aluminium Industrial Cell Designs. He worked for Syntec between 1997 and 2014, and the last 10 years he was Executive Vice President for the Research Institute Syntec Materials and Chemistry. He has a long experience in technology communication processes, including numerous board positions in new and established companies, as well as being the exploitation manager in both Horizon 2020 Innovation Action Super PV and CSL pilots. So what we expect today from these projects and these presentations is that they'll be showing how innovative European PV and PV-related products are becoming financially competitive on the global market, particularly the solutions which are coming from these 3 projects. This is what we want to learn today. So having said that, I think we can actually go already to the first presentation from Elena. Elena, can you take over the...
Yeah, thank you, Monica. I just need to find out how I can share my screen here.
Oh, just there is the monitor, just you click there. Once you click there, you just share the entire screen so that they can see your image, your face, and also the presentation in presentation mode, okay, in PowerPoint.
Is it working now?
Yes, if you can insert in. Perfect, thank you.
Okay, perfect. Yeah, so my presentation will be related to BIPV Boost project and presenting how BIPV is or is becoming a competitive technology in Europe. So I would just give a brief overview of the BIPV Boost project, provide some explanation and insights on what is BIPV, before showing how does current BIPV competitiveness stand today, and presenting some innovation of the BIPV Boost project, which contribute or will contribute to bring down the costs of BIPV, and then showing a more global overview of the perspectives for BIPV competitiveness, building on BIPV Boost innovation, but not only. So BIPV Boost is a Horizon 2020 project. It's a project that started in 2018 and is scheduled for 4 years.
Okay, sorry, Elina. At least for me, I cannot see. I just can see the first slide. I don't know if it is. Okay. In presentation mode, okay. Okay, I don't know why. Maybe you were talking, so I could not see the other slide. Sorry.
Sorry, Elina. Do you have two screens while
No.
you're working? No, so it's weird because I don't see the presentation mode. I only see the normal mode.
And now do you see the slide?
But not in presentation mode, actually, no? Monica.
Yeah.
So maybe you can just switch off again the monitor, the share screen. Add it again with the entire screen.
Okay,
Yes,
what
perfect.
about now? Okay, perfect.
Now it works.
Okay. So the consortium for BIPV Boost is composed of 19 partners from 7 European countries, and they are both researchers and industrial partners in this project. Overall, what BIPV Boost tackles is to bring down the cost of BIPV, to bring those costs down all along the value chain. And the general objective is to be able then to spread the message of BIPV as a flexible, reliable, and cost-effective technology. And this message should be vehicled to the whole BIPV community. So that is, of course, BIPV technology providers, but also members from the construction sectors, architects, designers, also policymakers. So that's it for the general objectives of this Horizon 2020 project. So then what is exactly BIPV? So BIPV means building integrated photovoltaic and is opposed to BAPV, which is building applied photovoltaic. So here the BIPV system really takes over the function not only of an electricity generation unit, but also as a construction material. And thus it also needs to have to meet the requirements in terms of load resistance, fire resistance, all the requirements that a conventional construction material would need to meet. And it can be integrated to facades, to roofs, also to more original surface, for example, balustrades, carports. These are all possibilities to integrate BIPV. And it can be found under very different aesthetics. So in terms of transparency, different possibilities exist, but also in terms of colors and patterns. So BIPV is really offers a really wide range of possibilities. The most, let's say, standardized version would be in-roof mounting BIPV system. In this case, there's a special mounting structures that allow us to use conventional PV modules. So that would be the most standardized and simplest, let's say, BIPV version, all the way through more colored version, transparent versions, also BIPV products with patterns. And in this case, it's custom PV cells and modules that are used. So if we want to have a look at today's competitiveness of BIPV, because BIPV is both an electricity generation unit and a construction system, there are really different levels at which the competitiveness of BIPV can be assessed. The first perimeter would be to assess its competitiveness as a construction material. In that case, the typical metric that would be used are euros per square meters, and one would compare the BIPV construction material cost to other conventional materials such as ceramic tiles, for example, or concrete, glass, wood, or any ready construction material. Then we can move to a slightly larger perimeter to the construction system. In that case, for the BIPV system, we also take into account the cost of the inverter, cables, the mounting structures, the installation costs. And in that case, we can still compare to other construction systems, such as a whole ceramic tiles roof or the installation of a glass facade. If we switch to the second function of BIPV, we can also have a look at how does BIPV perform in terms of competitiveness to produce electricity. In that case, based on euros per kilowatt hour, we can compare to the cost for other technologies such as BIPV, but we can also make the comparison with retail grid electricity prices. And finally, if we want to take a more holistic approach and evaluate the competitiveness of BIPV as a project or as an investment, in that case, the typical metric will be the net present value. And here what we want to compare is investing in a BIPV system versus investing in a conventional construction system. So here we have the first overview of the system level perimeter, and with the comparison made for roof system on the top and for facade systems on the bottom. Overall, what can be said is that the simplest BIPV solution, so here, for example, we have the in-roof mounting system, which can use conventional PV modules. This type of BIPV system can compete with regular roofing system, but overall, if we compare active BIPV solution with conventional alternatives and equivalent alternatives, the system cost of BIPV will be higher. But it should be added to nuance those comparison that BIPV also comes with this additional functionality of being able to produce electricity. And so this expectedly leads to higher costs. This is the first thing. The second thing is that the active solution, active BIPV solution, are typically more interesting from an economic point of view than the subsequent application of BIPV on a regular roofing solution. And this is because there are some costs, like the installation costs, that are mutualized, and so overall costs are lower. If we want to have this more holistic competitiveness assessment, this means we have to look at all the revenues and all the costs that are associated with a BIPV project. In that case, in terms of revenue, we'll have, of course, savings on the electricity bill for each kilowatt hour that is self-consumed. And more precisely, for each kilowatt hour that is self-consumed from the BIPV system, one can make savings of up to the compensable retail price. So that is the part of the retail electricity price that is directly proportional to kilowatt hours consumed. This is the first source of revenue. The second source of revenues are any subsidies, incentives, or any possibility to value injected electricity to the grid. And this really depends on the country. We'll have very diversified types of support schemes. And then in terms of costs, since we want to compare investing in a BIPV system versus investing in a competing conventional building envelope, what we consider as the initial investment for BIPV is only the extra cost compared to the conventional solution. And for that purpose, the total end-user cost of BIPV is broken down into its different components, and then for each component, we can determine what part of the component is specifically attributable to BIPV. And so this resulting extra cost of BIPV compared to the conventional solution is taken as an initial investment. And then we also have, of course, various operation and maintenance costs. And so all these costs and revenues are summarized into cash flows, so allowing to calculate the net present value over 30 years. And in the end, it's normalized by the installed surface. So there are different factors that can affect the competitiveness results of BIPV. First, also, of course, there are many country-specific factors. For example, what are the irrigation conditions in one country? Are the available support scheme attractive or not? Are there any BIPV-specific support schemes, for example? And also, how are the retail electricity prices for the different customer segments? There are also factors that relate to the BIPV system in itself. So that would be how much is the extra cost of the BIPV system, how is it tilted and oriented, and what is the system power density. So here we have the results of current competitiveness that is achieved for different BIPV systems. So here we have the example of two residential systems, a multi-family house and a single-family house. And overall results here are quite attractive for the single-family house and quite encouraging for multi-family houses. And this is because, for example, single-family houses, there's really a combination of favorable factors, such as high retail electricity prices. Of course, there are differences depending on the country, but overall, for residential customers, retail electricity prices are higher. We also are here in the case of a opaque BIPV solution, so the power density of the system is quite high, and we are also in a configuration of a tilted roof, so allowing to capture good irradiation conditions. Here in the multifamily house configuration, we also have high retail electricity prices, good system power density, but because the system is integrated to the facade, irradiation conditions are overall not so optimal. We have here two further reference cases for which we have calculated the competitiveness, an industrial building and an office building. So what is interesting to show here for the office building is at least in the configuration that we chose, that is a semi-transparent facade BIPV system, it's already a combination of several unfavorable factors, being that for commercial customers, only medium retail electricity prices can be expected, so savings on the electricity bill are not so important. And since we have a vertical tilt and also only low system power density, the generated electricity is quite low. So in the VIPV Boost project, as mentioned below, the idea is to tackle the cost reduction for BIPV and to do this all along the value chain. So here it's just really a general overview, and with the small BIPV Boost logos, you can see what are the different steps of the value chain which are somehow tackled by BIPV Boost. And I have here 4 examples that show what is developed in this project. The first concerns the manufacturing, so flexible and automatic BIPV module manufacturing are developed. Here, it's really the idea of this manufacturing line is, on one hand, to be compatible with a wide range of cells, types, and sizes, and also to have the most automatic steps as possible. And by doing this, it will reduce the manpower needs, but also if it's more automatic, then the failure rates can also be reduced. So here it's the module manufacturing cost that is tackled with reduction of this cost being the objective. We have also development of aesthetically advanced glass BIPV products. So this innovation encompasses the development of colored products, pattern products, bifacial products that can be integrated to balustrades, for example. And here it's the end user cost that will be reduced, mainly through more cost-efficient coloring or patterning techniques. Also on the software side, there is a BIM software that is developed within the project. So the name of the software is BIM Solar. And so the software combines both everything, all the features that could be found for PV software, so electricity production optimization, economic indicators, and also all the advantages of BIM software. And here the main focus is again reduce the end user cost through reduced times needed for the design and collaboration between the different stakeholders. And the last one is on the system side. So here the idea is to again reduce end user costs, but by focusing on easier installation thanks to lighter modules, for example. These were BIPV Boost innovations, at least some examples of BIPV Boost innovations, but there are also plenty others external improvement that will also benefit to BIPV. And this can arise from the PV sector, from the construction sector, or from the BIPV sector as a whole. And all of these individual improvements will be essential for BIPV, but will only be the full impact of those innovation will only be met if there really is a market pull and technology push to effectively achieve all the individual impacts of those innovations. So building on those BIPV Boost and non-BIPV Boost improvements, we can somehow plot a roadmap for BIPV competitiveness in Europe. So overall, for the single-family house that is currently already competitive. The different improvements will further enhance this competitiveness. For multifamily houses, it can be expected that based on the different innovation around 2025, competitiveness should be reached and largely reached in all, almost all studied locations. Approximately the same conclusion can be made for industrial buildings with competitiveness threshold reached by 2025 or 2030, depending on the local conditions. And for the office building, which was the one with the most mitigated or most negative competitiveness results, it can be seen that by through market pull and technology push, both from the BIPV Boost project and also external improvements, the competitiveness of this type of configuration can become positive by 2025 in Southern Europe, where better irradiation conditions are met, or 2030 for all remaining countries. So just some key takeaways, and then I think I'll have passed the time. BIPV really is an opportunity to and offers a wide range of possibilities in terms of the area it can be integrated to, in terms of designs, in terms of colors, transparency. And it's already competitive in some segments and some locations. Then the different innovation that will be developed or are currently developed in BIPV Boost, they will significantly contribute to further reduce the cost of BIPV solution. And this, along with other improvements from the PV, BIPV, and construction sectors, will also further improve competitiveness, and overall the general perspectives for BIPV on the short to medium term are quite good for all types of BIPV and all European locations studied here. That's it for my presentation. You can also visit the BIPV Boost website, where there are plenty of deliverables and additional information.
Thank you, Alina. So we're going to go now to the presentation from Fabricio. He'll be presenting energy matching, and I didn't mention it before. Basically, energy matching is a project where he'll be sharing more information about it, but the idea is to look at how adaptable renewables can envelope buildings and maximize energy harvesting to optimize the U building and district loads matching. So I give you the floor.
Thank you so much. First, thank you so much, Monica. Can you see my screen, please? In the presentation mode? Okay, yes. Perfect. So, okay, let's start. So thank you for the project introduction. Monica, just I would like just to mention also that the overall objective of the project is to maximize the renewable energy source harvesting in the built environment, in order to demonstrate, to develop and demonstrate cost-effective active building skill solution together as a part of optimized building energy system. Also, the idea of the project, the main overall objective is also to be connected with the all local energy grid and manage also a district energy hub, including also implementing optimized control strategy with a comprehensive economic rational balancing objective and performance target both private and public stakeholders. So this is basically the overall objective of the project. The main objective, let's say there are three. A part of the to define and develop adaptive envelope solution for the energy harvesting at building level. It's also to integrate this solution into the building and district energy concept. And the last one, a specific objective, let's say it's a geoclusterization of solution and replication potentiality. So, having a first introduction to the project, let's go directly to the exploitable result. we identify 7 explodable results. In total, there are 17 explodable results. The key one, there are 7. The first 4, the first 2 explodable results, they are software, basically, the energy matching platform, energy matching tool, that they help for the BIPV in the phase of design of the buildings. They help to optimize the BIPV position, the economic and the environmental performance of the system. So I would just remind that after this, in the next section, next paper section, there is District of Tomorrow, the session, which will be presented by our colleague Jennifer Adami, the energy matching platform. Then you will have a clear overview of this case explodable result. So a part of it, as we mentioned, it's a kind of holistic solution. What we are proposing energy matching, there are also the Versailles Kick-Go substructure that you should go together with the BIPV system. BIPV click and go from Onyx, which it is integrated also the composite BIPV from Tecnalia. And then also we have the solar window blocks developed by Finestra, which is innovative solar window blocks with more also aesthetic design and cost, let's say, cost reduced in comparison to the cost, and also environmental, like energy performance optimization in comparison to traditional windows. Then there is also the packages related to the harvesting packages, which include the dual source heat pump, the solar water source, and also the methodology to integrate these two explodable results. And then there is the building the district energy harvesting management system, which is developed for RAMP with the help of the HDA. So these are the block of technology that we would like to we have developed in energy matching. They are actually currently testing in the demo site, and the final TRL is 7. So it's a high TRL, but not really reached the market yet. So for the pilot, we have actually 4 pilots. We started with 3 pilots. One is the pilot in France, which deals with multifamily dwelling units built in 1969 and existing in 1988, which includes 22 residential units over 1 basement, plus 7 stories combined in the first construction of the station. The second is the Comune in Campi Bisenzio in Italy, which is also a kind of social house, let's say, composed of multifamily dwelling unit built in 1984, which include 12 residential units over different floors with also some common areas. The third one is the Ludvika in Sweden, demo site, which is the multifamily dwelling unit made of 3 buildings in 1973. And we have actually another demo site in the Netherlands, which has been integrated into the project from July 2021. And as you will see in the next slide, we haven't studied really the impact of this demo site, of the energy matching technology of this demo site. So we still ongoing let's say the activation and the construction of the demo site. While on the others there is Campo Bisenzio is already over. In France also the activities are almost finalized. The Ludvika, they are in the middle, let's say. So here in this, once that we had an overview of the project, what we will discuss in this presentation is the energy matching business model. Then we go to 2 interesting studies that we have done here in the framework of an energy matching exploitation activities, which is the ESCO research and the energy matching Italian demo case cost assessment. So we go now to the business model. We identified 3 customer segments for the business model of the energy match. One are the public BD owners, the other are the ESCO, and the other are the real estate. Once identified this free customer segment. Then we propose the value proposition. We create the value proposition of the energy matching block of technology, let's say, to be commercialized in block. And then we, following the methodology, the business model canvas, then we create the value proposition, including the product, services, the gain generators, and per release. On the other hand, we try to identify the customer canvas of this free customer segment, and we have identified the customer jobs. So which type of jobs they will do the product and services for the value proposition, the gains and the pain. So then we studied how the value proposition of the energy matching solutions, they fit with each gain and pains a customer. So the customer canvas. So this is actually, it's the business model canvas template, which we have done for the free customer segment. And this is an example of the business model. So this is the value proposition for the energy matching solutions, which are high energy performance and easy to replicate. The solution with they are really with easy maintenance. This is a really strong point of the majority of the energy matching solutions. An effective energy margin system, fast, easy installation. This is also it's true for the substrate developed BIPV substrate developed by Tulips. The RES bus system, the pre-manufactured retrofit, the unique synergy of energy management, and the significant improvement of the building prestige once that all these solutions have been developed. And this is the value proposition. Then we create the other block of the business model canvas. So it was a really long activities. Then once that we identify this type of activity for each segment, then we move to the other point of the energy matching exploitable solutions activity that we have done, which are the business cases on the free pilots. We had these free pilots, one in Italy, in France, Sweden. We identify some, let's say, actors, which it can be kind of intermediate, that they could act as a main beneficiary of this business case and trying to benefit from this business case on the free pilots. So if we go in details, just on the business case, we also identified the cost-benefit analysis. So the methodology was to assess also the CapEx and the OpEx together with the benefits assessment, which are countable, the benefits, but also there are also some uncountable benefits which has not been quantified, but we have also to take into consideration in the final, let's say, impact assessment. These are let's say the structure of the CapEx or the OpEx, which this is the case for the Italian case. It includes some equipment, the consultants, the software licenses, the research development, marketing, and administration and travel for the Italian demo case, for the Italian business case. Then also the benefit, this is, let's say, another case for the business case of the Italian business case, which are two types, let's say, that are transaction-based benefit and the management base. So if we go toward the methodology will be applied after we calculate the discount payback period and the internal rate of return, which is an iterative equation on Excel to see if how will be the investment, there will be the return on the investment, how will be, and the discount payback periods, how will be the years where the investment have been covered. So we have this kind of two mathematical formula to apply in our study for each business case. Then we go directly on the approach that we had for the Italian business case. It is the ESCO approach. So we assess the viability of the project from the point of view of the service company, which bring the energy match package to the market, reaching the select customers. So we made the kind of lifetime here for 7 years. Okay, we assume that the lifetime was 7 years for a potential retrofit project at commercial level. For the other business case, we put as approach the construction company, because big our industrial partner construction company, and we assess the viability of the project from the point of view of the construction company, which bring the energy matching package to the market, reach the selected customers. Also here in this case, we agree for a lifetime of 7 years. For the other business case, the third one, which is on the Ludwig business case, then we made unfortunately Ludwig lost the license for the energy sales in Sweden. Then we had another type of approach, which is the retrofit scenario. So once the idea was to assess the viability of the project from the point of view of retrofit scenario by evaluating the actual benefit obtained by installing the energy matching solution. So then we had 2 different cases inside the Sweden case, and then we realized that we made 2 assumptions related to the package retrofitting on the switch demo case related to the building attached photovoltaic. And the others was related to the BIPV, which the building, the BIPV approach, so the integrated approach, which is different, as you know, from the attached photovoltaic. And in this case, the business case has a lifetime of 30 years. Now we go to the result. And this is the result that come up from the study that we did in the project. For the Italian, we had a discount payback period of 4 years, which an internal return of investment of 31%, which is really good in terms of investment profitable of the investment. For the France case, we have 4 for payback time, for discounted payback time, while for internal return of investment is 19. So if let's say that it's not so profitable for let's say in the long term, but there is a payback time that you can cover it in 4 years. That's it's interesting to see how the different scenario that we had for the Swedish one, which is the BIPV approach, which is BIPV approach, which has a discount period 23.4, while an internal rate of return of 2.5, which is clear not profitable and not really convenient for a retrofitting point of view. Then in case we go for the integrated approach for the BIPV, then we have a payback time of 4.8 and internal rate of return of 28, which make profitable once that you do, you have to retrofit the demo case in Sweden, and then you will save also money for the cladding, for the facade, the other type of materials that will not use it in this retrofitting scenario. So these are the business case of the result. Then we have a carry on an ESC assessment of this of the 3 countries that we had the demo case, to see how can be considered as stakeholder for an energy matching project technology. So the ESCOs for us are really important as an intermediary of our technology to bring them to the market. And then we made a type of analysis of the ESCO assessment for each 3 countries. So if we go to Italy scenario, so first we have around among 1,500 companies registered as an energy service enterprise, which is in 2019 there were 379 certified ESCO under the standard UNISEI. Then also there are also the Politecnico Milano that carry out the study, which over 300 ESCO companies have been interviewed, and the following result they were collected. First, among these ESCO, 20% only work in the industrial sector, while 10% only work in the civil sector, 70% work on the both sector. Then in the civil sector, it's interesting to see that 54% of the ESCO were in the residential one. And another important thing that from the study is that in 2018, the ESCO in Italy has a turnover of 2 billion euro. If we go on a deep analysis of the Italian ESCO market, we see that ESCO intervention can cover all the aspects of retrofit, from the envelope to the maintenance. And also that, fortunately, the COVID-19 represents a strong value for the future, but there are some green incentives that makes the ESCO market in Italy really, really active. So the Italian government, they have, let's say, a lot of incentive schemes. And the best one, for my point of view, is the super bonus, which is 110% tax deduction of the expenses in 5 years for the realization of energy efficient intervention, mainly for condominiums, but also include also envelope system and renewable. So you can also condominiums, but also for some single resident unit or other type of buildings. It's true that this it covers more than the cost, covers everything, the super bonus, but there are also some specific boundaries conditions that the building retrofit has to have to be included into this incentive scheme, which is the type of building, the retrofit type, the installed technologies, and the forest inexpensive. So above the forest inexpensive is not possible to use this scheme. So the others are the conto termico, which it cover each more for small-scale thermal energy production, and it cover the 65% of the all expensive incurred. And the other also is the eco bonus, which enable more private individuals, companies, they took a part of cost incurred for carry out energy efficiency upgrade project. While that super bonus and conto termico is more applied to public institute, the super bonus can be applied for public and private. For France 1, the ESCO market in France is considered one of the largest, most growing one in Europe. Total market volume is equal to 30.5 billion euro. And the main service related to ESCO is the analysis of the asset, studies, engineering, installation, operation, maintenance. Now, at the moment, there are 350 companies working as ESCO, which among which 10 have the guarantee agreement. And let's say that average size on investment of ESCO contracts is between 1 and 5 billion. And there are also two types of contracts, let's say, that are the APC, the energy performance contract, ESC, that is energy supply contracting. And they have some different contract agreement for these two types. If we go to Sweden, here the situation is more, let's say, is more pessimistic. In Sweden, there are currently 240 companies working in the energy efficiency sector with a turnover around 3 billion euro, while there is a limited number among these that can be classified as ESCO. Apart that is the market is a bit, let's say, moderately sided fluctuating, which can be also, let's say, a bit even a bit in decreasing the amount of the ESCO project in the last 5 years. There are also, let's say, we go to the actual market size of ESCO in Sweden, which is around 68 million euro, which is different that for the amounts that generate in the previous countries, in Italy and France. Around 50% of the contract regulated to properties. The typical intervention in the ESCO here as a building as a wall, HVAC, automation control. The typical investor varies also between 2,000 euros, 5 million, and the ESCO company can be divided in 3 main categories, which can be building control, automation control, manufacturing. So there was a study from the European Union. This is, let's say, an overview of the ESCO market. How is the situation in Europe? This is in 2018. So we can see that Italy has a really high market growth for the ESCO. France is also in the good shape, while Sweden is the only country, according to the European research, ESCO market development between 2015 and 18. It's decreasing actually the amount of the market. And also because in Sweden there are just 10% of PV subsidy incentive just for the retrofitting approach. Then we go to the Italian demo case cost assessment, which is basically, it's another sample that we made for the Italian demo case to assess the impact that we had it in the Italian demo case. So in RHM, we analyze how is the price for the, let's say, market analysis with the average retrofitting price assessment according to some parameters, which can be the location, destination use, the building geometry, the energy demand, the installed technology, the investment cost, the performance target. And the prices for per meter square per euro is 555,41 for a commercial project for retrofitting commercial project. Then we analyze how is an energy match retrofit potential retrofit cost assessment of Italian demo case, and we had 3 types of configurations, and we came up that with energy matching extra work, we have 719,07 of cost, total cost of potential retrofitting assessment for the Italian demo case. Then we finalized the studies on the impact that energy matching solution had on the Italian demo case, that there is basically, take it the reference, the benchmark market, there is an increase of 23% of the total cost with extra work, okay? Extra work means that some work they're not ready to energy matching solution, but you need to do, for example, to cover all the buildings, other type of activity that are not linked to the energy matching solution. There is an increase of 23% according to the benchmark reference. Then we had some different type of block of technology configuration, we call the free one. One that is the PV panels part of substructure, which we have an increase of 13%. The other is with the market window block, the solar window block, with an increase of 70%. And the other is with heat pump without solar wall, including also the PV panels. Then it's an increase of 30% of the cost, but let's say the analysis was also interesting for the energy point of view, which is the energy consumption, the energy production is higher. So we come up that there is the best configuration is the third one. So I will conclude with the lesson learned. What we have learned for the business case, and with business case we have learned that it's crucial to have a synergy between all the actors in a commercial but also demo renovation project. This seems quite, let's say, logic, but in the real world it's not so easy to find the kind of synergy between actors. And also that the ESCO market, financial incentive, regulatory and political framework different in each EU countries. This implies also the different solution for each specific scenario. So what is good for Sweden is not good for Italy. And then some financial incentive that the Italian government with the major, let's say, financial incentive can cover 100% of the total cost of a retrofitting project, while in Sweden there are not really complex, according to our Swedish partner, complex retrofitting incentives. There is just 10% of PV support, financial incentive for the installation of the PV, which seems to be increased in the coming years. But then it will be more difficult to apply to have some retrofitting cost in Sweden. So that's all from my side. I'm 3 minutes late, assume.
Thank you, Fabricio, for presenting all the interesting results from energy matching. We're now going to switch to the presentation from Torsten with the Super PV project. Super PV is about developing superior quality PV systems, which are based on combining technological innovations and business operation solutions for the large-scale deployment of PV in Europe. So, Torsten, having said that, I will leave you the floor. If you can share your screen, please.
Hello, do you see my screen?
Yes, we see the one with the sustainable places now. If you can, yes, now it's working.
You see the PowerPoint now?
Thank you.
Okay. What happened now? Yeah. So switching to slide number 2. Do you see slide number 2?
Yeah, we see the slide with the content now.
Yeah. Just checking. Okay, I will present Super PV innovations and approach to business model development. Thank you for the introduction and for the opportunity. So first I will give a very short project overview and organization for implementing the project exploitation strategy. I will talk about market disruptions related to conceptual models for innovation and interaction. And finally, being a bit more concrete on Super PV innovations. What are the key questions at this stage and status and business model opportunities? First, this is a Horizon 2020 innovation action with 26 partners. Started in May 18 and will end by October next year. So it's a large project with many partners going after an ambitious but we think realistic goal for innovative PV system cost reduction, with where the key is LCOE reduction of the levelized cost of energy. By following 3 technological and data management innovations along 3 axes. We have PV module innovations, power electronic innovations, and system integration innovations. One important thing is that the upstream parts of the solar supply chain, solar cells and upstream from that, are not a part of the project scope. The organization for implementing the exploitation strategy was established already from the start, actually in the proposal. There is a so-called exploitation team where a representative set of partners is included, and we are overseeing technology and market watch, market analysis, business case modeling, market replication strategy, and exploitation risk assessment. Now, the exploitation team delivers a presentation at every biannual project meeting with an update on these topics. And the final findings and recommendations from this team will be summarized in the Super PV exploitation strategy. And the strategy is actually how to get from mostly TRL 7 at project end to TRL 9 commercial level after the project. And so thus the final exploitation strategy will serve as the business plan for exploiting the project results. Now a bit about market disruptions. What we experienced already at the beginning, in the months from the Horizon 2020 proposal submission in the 3rd quarter of 2017 to project start in 2nd quarter of 2018, there was about 40% price reduction of solar cells in that period. But before we respond to this question, we need some contextual background related to innovation processes, open versus closed innovation. To the left here, we see the traditional closed innovation model. There's a funnel, innovation funnel here, starting with ideas, which are matured, and finally something useful for the market. That is an innovation. The open innovation model is here, and here we see there are holes in the funnel, both allowing external ideas to come in and also some ideas to get out. So the traditional model of innovation was closed and linear with a clear focus on the defined market. And so this is a classic technology push model from starting with research, R&D, development to new product and services. The open innovation model, on the other hand, makes much greater use of external ideas and technologies, and in turn lets unused ideas be used by others. It should not be confused with defocus. You still have a focus, but you allow both new ideas, but you also allow for ideas not being used in a core market to survive. And this is from Chesbro, 2003. Henry Chesbro, he was the one that invented or coined the term open innovation. A very important principle in closed innovation for industrial companies. The smart people in our field work for us. Open innovation, not all the smart people work for us. We need to work with smart people inside and outside our company. And concerning intellectual property, we should control our innovation process so that our competitors don't profit from our ideas. Or in open innovation, we should profit from others' use of our innovation process, and we should buy others' intellectual property whenever it advances our own business model. Another way of looking at innovation is through the innovation chain, from education to research to new innovation, and finally to be exploited by new or established industry. In this model, the chain is as strong as the weakest link. Fortunately, however, innovation processes are hardly ever linear. And here we see a more realistic picture of modern innovation processes that occur increasingly in networks through non-linear interaction between different actors, from researchers to entrepreneurs, users, governments, and civil society. Much more robust than the traditional linear model. And indeed, Horizon 2020 innovation actions like the Super PV project, and also I think the two other projects in this seminar, are built upon this principle of open innovation, open science, open to the world. Now, back to the question, how to deal with dramatic price reductions in the market already before the project started. This huge price reduction of solar cell price. And the Super PV response is that, okay, the upstream silicon value chain is not a part of the project, hence cheaper solar cells in the market is actually an advantage for Super PV innovations. Similarly with other innovations outside the project scope. And in the open innovation paradigm, one should optimize usage of external technologies and know-how. Secondly, several Super PV innovations are targeting enhanced energy yield or performance ratio, and are even more beneficial when the solar cell efficiency increases, as it has a tendency to do and will continue to do. Here we see the latest edition of ITR-PV, International Technology Roadmap for Photovoltaics. So solar cell efficiency will continue to increase, which gives even more value to Super PV innovations. Finally now, on the concrete project, key questions at this stage. How to establish an intellectual property management strategy. Intellectual property management can be viewed as a series of interrelated processes, from identification to identify, evaluate, protect, and, if necessary, defend and exploit. So, identification and evaluation we do through a comprehensive description of key exploitable results. And there are many questions in this key exploitable results description. Some central ones. What is the expected TRL at project end? What is the anticipated time and cost to reach TRL 9 after project end? Are clear value propositions formulated for different innovations and markets? Is a motivated exploiter of a given key exploitable result identified? And are the first prospective users of a key exploitable result identified? We also look at available services from the European Commission, such as the results booster. They have 3 services: 2 services related to exploitation, service 2 business model development, and service 3 go-to-market support. We think we need to meet 3 criteria for applying booster support for exploitation, or that is our recommendation to innovators in our project. First, of course, you need a comprehensive description of the key exploitable result. You need a motivated exploiter in place, and the exploiter needs guiding toward exploitation. If you already know how to do it, just do it. Don't apply for support. And here we see status at month 36. We have several innovations with expected TRL larger or equal to 6 and anticipated time to market less than 3 years after project end. Altogether 10 innovations. We unfortunately don't have time to go through them now. But anyway, most innovations do have an intended first commercial user already present in the Super PV consortium. Still, for some innovations, the first customer is not yet identified, and in some cases, a motivated commercial exploiter is not found at this point. So we still have some work to do, and that is good. Over to integral assessments. New prospective innovations from Super PV combined with price reductions and improvements elsewhere in the PV supply chain can form winning combinations in the market, leading to substantial LCOE reductions, even much larger than originally targeted. Here we see the original targeted reduction in LCOE, 37% down. And here, if we combine improvements outside the scope of the project that are available in the market with Super PV innovations, we can achieve total LCOE reduction of 57%. And here we have compared LCOE with projected market benchmark for 2021, the solid line, and 2023, the started line. So altogether, the so-called Super PV best estimate, Super PV innovations plus market improvements is competitive. So this may point towards a flexible business model for non-vertically integrated module manufacturers and PV plant developers, provided that they can capitalize on cost reductions not covered in-house, meaning that they are, in the real world, able to apply open innovation practice. To conclude, we have briefly gone through the exploitation strategy for the project, and the importance of open innovation practice is discussed. Business models for market uptake of individual innovations are, as we speak, under development. A great advantage in this regard for several innovations is that the Super PV consortium includes both innovators and prospective first commercial users. New prospective innovations from Super PV combined with price reductions and improvements elsewhere in the PV supply chain can form winning combinations in the market, leading to substantial LCOE reductions. And I will repeat that this may point towards a flexible business model for non-vertically integrated manufacturers and plant developers. But then they must be able to apply open innovation practice. Overall, the results from Super PV are at this point promising. Key remaining activities are to extract field data at the different Super PV demo sites in Lithuania, Norway, Spain, Tunisia, and Morocco, to ensure final validation of performance and to prepare business models and plans for market uptake after project end. Thank you for your attention.
Thank you, Thorstein, for the nice presentation about the different, let's say, working practices for research. For our panel session right now with open questions, I do not see, and Fabricio, maybe you know about this better than I do, if there are some questions from the audience.
Oh, they should be in chat, but it seems there are no questions, so feel free from the audience if you would like to raise some questions to write on the chat.
Yes.
Okay.
I have a lot of background noise, but well, I'm going to start with Darsten because it was the last presentation. So in the time that maybe some people have some questions for you guys, it's like in an environment where you have companies which are working in a closed research way and closed innovation, how do you combine that with open innovation principles? Because the idea, if I get it correctly, is that you can buy IP from certain companies to move forward with innovation practices. But how do you combine it when you have these environments where people are developing solutions in a closed innovation environment?
Okay, our company is really working with closed innovation practices anymore. I'm not sure, because you know, in say Horizon 2020 projects, EU projects, competing companies do take part in the same project, and they still have their core business, they still have their intellectual property, but they are willing to share, but they will not share everything. And that's why we have consortium agreements and grant agreements. Especially the consortium agreement in the Horizon 2020 project is crucial in order to define what are we willing not to share and what are we willing to share. And so very important in this context is also how will we treat results? Who will own the results? Who will exploit the results? So I think companies that are used to work in a closed innovation environment get a really good learning by working in Horizon 20 and similar ecosystems. Yeah.
And how does it work when you're collaborating with companies which are in other countries where they have low IP protection?
Okay, then that you should do with caution, of course, because it boils down not only to agreements, but you need to have mutual trust. But if you don't have a trust in the other partner, then you should not collaborate. But of course, there are also some formal precautions. If you're going to work with a company from a country where the regulations are not very strong, then you should of course select a country, say a neutral country. If say a company from Norway should work with a company from China, maybe China is a random example, then maybe we would opt for Belgian law. Okay, you see my point? So then you should have strong legal framework when working with companies from not so well regulated countries. But that's the one thing, and the other thing, you need to have a mutual trust in the other partner, regardless on where that other company comes from, I think.
Yeah, thank you. I have a question which is both for Alina and Fabricio. Maybe starting with Alina, it's like, what do you think it's currently holding back the economies of scale in European BIPV?
Yep, so there are several arguments that can be put up here. First is that the BIPV market is still limited, still a niche market, so the demand is not that high that it would really put pressure to have higher, or let's say bigger industrial manufacturing sites. That's one thing. And then the other thing is, for BIPV, there's always really this compromise to find between customization and standardization, which would allow, let's say, wide-scale, massive industrialization. And this customization aspect of BIPV is also one of its strengths, because it then allows to have, really from an aesthetical point of view, really a wide range of possibilities. So this compromise to find between being able to have more massive production, but still being able to have this customization aspects is I think the two key points. And with the innovation in BIPV Boost on the manufacturing line, they are really trying to, on one hand, to be able to be compatible with different types of cells, different sizes of cells. So on this side, they're trying to be flexible, but also trying to have more automatic steps in the production line or manufacturing line. So yeah, I would say limited size of the market, and then this compromise to find between customization and standardization.
Thank you. Fabricio, what's your take? Why aren't all buildings covered with BIPV today?
Oh, okay. Just it is actually correct what Elina was mentioned, and it is linked also to my presentation. That it is difficult, for example, for some company, because we have a company like in our consortium, like Onyx, for example. We had some discussion as exploitation leader, and for them it's easy to commercialize the product in some countries, but not to the others, not to others. So, for example, it's a limitation in Europe, I would say. So, for example, it can be good to commercialize Onyx Solar in Spain, Italy, France, but then it would be difficult to commercialize in other countries, which the regulation is different, the customization and the buildings, let's say, are different, especially in, let's say, east of Europe. And is a bit, this is a limit, customization, also let's say, also the regulation for each country to integrate and to reach a kind of economic scale for BIPV. So the customization is for sure an opportunity, but then also increase the price somehow. Somehow the customization, of course, if you do some in the economic scale, like other countries have a possibility to do it, for example, because the regulation, bigger country, like China, USA, they have kind of regulation which are big, and similar, they can apply in different internal state of these two big economies. The regulation, they started the political framework, the incentives in those countries. This is not comparable to Europe. This is a kind of limitation for some companies to commercialize their products, the BIPV products, in one country to another in Europe. Then they should have kind of reselling in other companies. Then the market penetration is different. It's difficult. Apart also the economic condition, the climatic condition, they can be different as well. But it's something that we cannot control.
I'm having a technical issue.
Could you hear me, us, Monica?
I cannot hear you anymore. I don't know.
Hello? Could you hear me? Yes, I lost you. Yes.
I can hear you.
You can hear me?
Yes.
Yeah,
Okay.
I can hear you as well, but
Yes,
not Monica.
I think it's Monica this year.
Yeah. You have to use sign language. Okay. I guess she will rejoin.
Yeah.
So just a question to you, Fabricio. I was curious because I saw some of your references. I guess that was from the construction sector. That was from 2015 and even 2010. So is that reflecting a very slow dynamic in that sector? Because
in the ESCO, you mean the ESCO market?
Yeah, because in photovoltaics, a reference from 2010 would be ancient times. So
no. It's updated. This is just I don't know the reference actually, but I don't remember the reference that were there, but it's between 2016 and 2019. What we refer to the market, to the ESCO research, okay? And then the last slide, it's related to the overall approach, let's say, ESCO market. That is for the reference is 2019 and 2019 from a European Union studies.
Okay, yeah, good.
Okay, so that's the real value. Okay, in 2 years, it can change, but not dramatically. It's true that in Italy, for example, we improved let's say the market share we have because RHM is also an ESCO. So we have also some contact. We work with many ESCO. So the market could even increase about it. Okay.
I see.
So, okay. Just one question also to you, Torsten. So do you have also this type of approach to other type of project, this open innovation approach, to apply to other type of project? How are the partners reacting on it?
We are actually a partner in another large Horizon 2020 project, not on energy but on raw materials. And in that project, the key innovation to be targeted is a new method of making silicon metal. And 3 of the largest silicon producing companies in the world, Wacker, Dow Chemicals, and Elkem, are all partners in that project. So even if they have, of course, core IP on how they make silicon today, which is made from quartz and carbon, they are eager participants in this new project where we want to make silicon not from quartz and carbon, but from quartz and aluminium. So even if they have a core IP on how they do it today, this is not core IP, but this is of course a core market for them. So then, so that's a perfect example on how companies go together instead of competing to develop a new innovation. So and it's also true that the entire structure of the Horizon 2020 program with the innovations actions are based not least on open innovation principles. Because if you look at any innovation action in Horizon 2020, you need to have this network of stakeholders present in the project in order to succeed.
Yeah, there is actually this shift from, let's say, close to open innovation, which is true. But especially in Horizon Europe, then we should totally change, let's say, the methodology. But then also to apply, it's sometimes difficult because still the partner, they need to be coached in this type of ideas,
of course,
this type of approach. Not always the partners are able to, let's say, to follow this open innovation because they are afraid of sharing some important information, confidential information to other competitors. Sometimes they have competitors even in the same consortium.
Of course, and you should not confuse open with naive. One should not be open with what actually is a trade secret that gives you an advantage in the market. You should not share that. But I think when you are aware using this open innovation approach, it actually increases the awareness in the companies on what what do we need to protect? What kind of technologies do we develop that we don't really have use for, but maybe others can? And what technologies, concepts are important for us, but we are not the best? Where can we buy? So I think if you approach it correctly, then it raises the awareness in the companies on how to operate. And I think it's instrumental to success even more in the future, because if it gives a competitive advantage, then you should use it. I see Monica is back again.
Yeah.
We took over a bit while you were away, so
sorry,
please.
Technical glitch. Yes. Yeah, so I missed a little bit of the conversation. I'm sorry about that. Yeah, the other question that we have, it's like, in terms of BIPV, what would be required in order to make it more cost competitive already today?
I don't know if you're asking the question maybe to me, but BIPV's competitiveness still highly relies on the extra cost compared to conventional solution. The reason why I'm saying the extra cost and not just the cost of the solution in itself is that today it does only make sense to integrate BIPV at the time either of a renovation or of a new construction. There's no interest in integrating BIPV to a roof that is already has just been built, or that and that is why we always need to consider the option BIPV versus conventional construction system. And this is where the extra cost actually comes into the equation. So there's this first aspect of the extra cost, mainly driven by the module cost. So on the manufacturing side, there could be a further improvement to reduce the costs or to improve the efficiency, to have an overall lower cost per watt peak. And further aspect is also to try as much as possible to include the idea or the option of BIPV as early as possible in the development process, so that it avoids to have, let's say, non-essential discussion between the different stakeholders. If it's clear from the beginning on that BIPV could be foreseen as an option, then it just makes the whole design and development and technical design process much smoother and more efficient, and there's a lot of time that can be gained and therefore cost that can be reduced with regards to these aspects.
Monica, there is also one question actually in the question answer. If you go to question, there is one question from the audience.
Yeah, now I can see it. So thanks for the question. It's like, how would future competition of Chinese advances in BIPV manufacturing influence current European business models?
Yeah, difficult question. I think we can expect the same general influence than for PV in general. It could bring down the cost for maybe more simpler, more low-end solution, but for the more high-end BIPV solution or very customized BIPV solution, I think the impact would be, it would be easier for European companies to compete on these segments. But it could flow the market with maybe lower cost, let's say simpler BIPV solution.
So we have 1 last minute for our session. I don't know if you want to make a final statement about, well, the session has been about innovative business models. So yeah, something about it from your projects.
Okay, just one fix that we haven't, let's say, discussed at the end. That is important, at least the financial schemes, the financial incentives. Okay, so Elina actually, she highlighted really well in her presentation, which let's say this extra cost could be covered sometime in some cases from the financial scheme, while in the meanwhile we can work on the cost reduction in the, let's say, short and medium long term. This could be a kind of solution, and not all countries, let's say, they have a kind of financial scheme complete to cover this part and to make, let's say, at least for the short and medium term, the market for the BIPV European producer more competitive in comparison to the other countries, which they have lower cost, even not only for BIPV but technology, but also for cost of labors, because sometimes we forget, but there are also some other costs related. So this, and at the same time also to use this financial incentive to retrofit some old buildings, which is starting to change, and also to change the paradigms to have kind of more producers buildings than consumers, just to change also the paradigm, to use also these financial incentives.
Yeah, thank you, Fabricio. So Thorsten, when from the big installations or in Super PV, what would you say?
In general or related to?
In terms of the business models, I mean, from your presentation, what I gather is that you're supporting to have more open innovation. So if you have one final statement about the status of the project and what you have learned from it, what would you say?
I think one key thing that we are currently working with is that we are very happy with some innovations, because we have the entire, say, ecosystem of or the value chain from idea to innovation to exploitation in place, but not in for all innovations. So it's very important to stress even harder that it's not enough to have a good idea and make a good innovation. It's not an innovation if you don't find anyone motivated to exploit it. So it's not only to find the customer, which is very important, of course, but you also need to identify the party that is going to do the exploitation, real exploitation, because that is hard work and needs dedication. So that cannot be underestimated and should even be stressed harder in future projects at an earlier stage, I think. Yeah.
Yeah, thank you. And Elina, one final statement for you, and then very quickly, please.
Yeah. So very quickly, I think that there are very promising innovation that will highly enhance the competitiveness of BIPV, and as you were saying, Fabricio, as the renovation rates increase as part of the renovation wave, and as part of, we consider more and more building as consumption points, also more than just production points, more than just consumption points. I think this will also stimulate the BIPV market and then allow more economies of scale, further enhancing competitiveness.
Well, thanks to all of you. I hope the viewers have had an interesting session, and I wish you a nice evening.
Thank you so much.
Thank you, Monica.
Everybody.
Thank you. Thanks to all of you.
Thank you.
Bye-bye.
Bye-bye.
Bye.